Hello and welcome back. Let's start off with an overview of what we've seen so far. We're starting out with a set of objects, S, of size n. Last time, we've been talking about k permutations. We can think of k permutations as lists with k objects, where each of the objects comes from S. And we're dealing with lists, so order matters. It matters what comes first, what comes second, what comes third, etc. And what we learned is that the number of k permutations is p of nk, which is n factorial over n minus k factorial. If instead we allow repetition, we have a sequence of objects from S of length k, which is an element of the Cartesian product of k copies of S, and the number of such sequences would be n to the k. Today we're going to talk about the case when we still have our set of objects S, and we want to choose k of them, but we want to choose k unordered objects from S. That will be the idea of a k subset or a k combination, and we'll be answering how many there are in this video and the next few videos. You'll need to come back later if you want to learn about how to choose k unordered objects where repetition is allowed. But for now, we're focusing on the question, in how many ways can you choose k objects out of n possible objects? Your gut reaction when you hear a question about choosing k objects out of n possible objects should be n choose k, which we'll write using this notation, with an n above a k surrounded by parentheses. So, if the question is, in how many ways can you choose 3 out of your 15 friends to go to a concert? The answer will be 15 choose 3. We're choosing 3 people out of 15. If you have a question that says, in how many ways can you choose 5 numbers out of 39? The answer is 39 choose 5, because there's 39 total possible objects and there's 5 that you're choosing. Or if the question is, in how many ways can you choose 2 different flavors of ice cream at a shop that has 31 flavors, the answer will be 31 choose 2. Simple as that. These types of objects, in which you're choosing some of a larger set of objects, are called k combinations. And in other places, you'll see notation that looks like this, c of nk or n ck. But in this class, we'll be using the notation n choose k. So this doesn't look like a number, and you might be asking, how can we compute n choose k? And we'll figure out a formula for n choose k based on k permutations. Start with the question. Given a set of n objects, in how many ways can we create an ordered list with k of these n objects without repetitions? These should look familiar. These are the k permutations of our set. The set has n elements, so there are p of nk ways to do this, and as a reminder, p of nk is n factorial divided by n minus k factorial. Let's compute this same number in a different way. We're creating an ordered list with k of these n objects. First, we'll choose which k objects we want to put in our list, and then we'll permute these k objects in all possible ways. By doing this, this will give us every list that we want once and only once, and so we're computing the k permutations of S in a different way. So, in how many ways can we choose k objects out of n? Our reflex says the answer is n choose k. Once we're given these k objects, in how many ways can we permute k objects? A permutation of k objects is calculated using k factorial. And so the total number of ways to count the number of lists is n choose k times k factorial. We can now solve this expression for n choose k, and we see that n choose k is equal to n factorial divided by k factorial divided by n minus k factorial. Let's apply this formula to the examples on the previous page. 15 choose 3 is 15 factorial over 3 factorial times 15 minus 3 factorial, or 15 factorial divided by 3 factorial divided by 12 factorial. We can simplify this expression by writing this as 15 times 14 times 13 times 12 times 11 down to 1, divided by 3 times 2 times 1 times 12 times 11 times 10 times 9 down to 1. We notice that a number of these factors divide to 1, and so we're left with 15 times 14 times 13 over 3 times 2 times 1, which when you calculate gives you 455. The number of Take 5 lottery tickets is 39 factorial divided by 5 factorial times 34 factorial, because that's 39 minus 5. When we write out this expression, we see 39 times 38 times 37 times 36 times 35 times 34 times 33 In the denominator we have 5 times 4 times 3 times 2 times 1 times 34 times 33 Again, a number of these factors divide out to 1, and so we're left with 39 times 38 times 37 times 36 times 35 divided by 5 times 4 times 3 times 2 times 1, which equals the particularly interesting number 575,757. And lastly, the number of ways you can choose 2 different flavors of ice cream at a shop with 31 flavors is 31 factorial divided by 2 factorial times 29 factorial. This we can simplify as 31 times 30 times 29 times 28 over 2 times 1 times 29 times 28 which is equal to 31 times 30 over 2, which is exactly 465. That's all for this video. See you next time.